Introduction to Machine Learning, EE769. Can you hear me?
Yes,
Yes, sir.
yes,
So,
sir.
Great. Yes. All right. Great. Welcome to the course. Go over what kind of things you need to do well in this course. So let's quickly cover why we study machine learning, why we make machines learn, or why make machines learn, right? So you all have heard a lot about ML these days, and some people think that ML is a fad. I don't think so. I think ML is going to fundamentally become a technology that stays with us going forward, just like internet or mobile, uh, or internal combustion engines or electric motors have stayed with us. Just like that, machine learning is here to stay. It's a it's going to be a change, a quantum change in the way our civilization and economies function using machine learning. So why do we want to make machines learn? So at so if you think about any model or any algorithm, it takes an input and it gives you an output. So here I have an index for that input. So let's say ith input gives you the ith output. Now, but these models, if we want to define them, it's very tedious to define them. So for example, let's say I have an algorithm for traveling salesman problem, right? So I have inputs and then I write the algorithm, which is the model, and gives you the output, which is basically it tells you that for a given coordinates of cities, what is the shortest path to touch every city exactly once and come back to the original city where you started, right? So that's a traveling salesman problem for which you can define an algorithm or a model that will give you, given an input, it will give you some output. But defining that model can be quite tedious in many cases. For simple models, we are not talking about simple models. If I talk about a simple model, then it may be very easy. So, an example of a simple model could be that let's say you have an input X and you have an output Y, and it is as simple as yi is equal to mx plus c. Okay, so this is also a model. So you give it an input x, and these two are the parameters of the model, and that gives you the output y. So it's a quite a simple model, but we are not talking about simple models. So let's say the models are quite complicated, or you can also call them functions, models, algorithms. These are all interchangeable in some sense. So some model that is yi is equal to f of xi, and I will parameterize with theta. Theta means like these are the things that are that govern the behavior of this function, such as m and c here, right? So this could be a much more complex mathematical expression, and it could even have um, if then else type of statements. If x is greater than this, then do that, then use this number, else use that number, etc., etc. So it can be quite tedious to actually define these models. And once you define the model is inflexible. You cannot change that model, right? Whereas given new information, you might want to change the model, and you might want a way to change the model. Okay, and many of these useful models are unknown, right? We can't precisely define them. So to give you an example of, if you are given an image, you want to find out whether it has a face or not. So what is an image? Image is a two-dimensional array of pixels, right? So you have all these columns and all these rows, and each value is a number from 0 to 255. Okay, so for this number, 0 to 255, so these are like discrete values of the pixel intensities. By just looking at this pixel grid of, let's say, size 64 by 64, how will you write an algorithm, or how will you write a model, or how will you write a function that tells you whether it is a face or not? So so it maps it to an outcome of 0 or 1. Okay, so this is 0 to 255, but times 64 times 64, right? So it's on a 64 by 64 grid. So you want to map it to 0 or 1. 0 means no face, 1 means face. That model is unknown, right? It's very difficult to type that model. Okay, but we may know something about the output. So what do you mean by knowing something about the output? In this example, it could be that for 10,000 images, I know that these 3,000 have faces and these 7,000 do not have faces. So I may know that about the model, right? Sorry, about the output. So the desired output for some training data, I might know about that. So basically, in machine learning, we will look at algorithms for discovering useful approximate models. So there are a lot of words here. You have to think about all these words. So we want to discover useful approximate models for complex mappings. So your problems has to be complex. The function that you are trying to model has to be complex. Only then machine learning is useful. If it is as simple as, let's say this is your earth, okay, and this is the trajectory of the moon, around orbit of the moon around the earth, and you want to predict where will moon be 13 days from now, right? That is for all practical purposes a simple mapping. It's an equation of a circle or it is an equation of an ellipse, right? And so this is all relative to the earth, but let's say we are not considering relative to the center of the galaxy or center of the universe, something as simple as relative to the earth, relative to the position of your town, whatever that is. So that is, in for all practical purposes, is not, that's not a complex mapping. Well, it depends on how precisely you want it. You want to also take into account how the moon changes the shape of the earth in terms of tides and all that. But if you want some coarse approximation within, let's say, plus minus a few kilometers, then it's probably a simple mapping, right? So for that, machine learning is not useful. Simple models, especially, let's say, for simplified physics, not like very precise physics where you have a lot of moving parts, but you make a lot of approximations. For that, the models are quite simple, the Newtonian type of physics. So for that, machine learning is not useful. Okay, so machine learning is about discovering algorithms. So for discovery, you need to look at inputs and outputs, and the model itself is not discovered. Okay, so your algorithm will discover the model, all right, and the model will be for a complex mapping, but the model will necessarily be approximate. Why will it be approximate? Because it is a model of a complex mapping. You don't know the precise mapping, so you will assume some mapping with some unknowns, and the algorithm will only resolve those unknowns within certain constraints. And those so if your original assumption about the structure of the model is wrong or it is not precise, then your approximation would be as crude as your as how imprecise your original how inappropriate your original choice of the model was. Okay, so these things will all come in later. Now the reason I mention all this is because this particular type of discovering of algorithms has applications in many fields, not just in face recognition or basically image processing and computer vision, but also several uh, services that you use today. For example, you can today use uh, speech to text on your phones right now. You can go to if you have an Android phone, you can go to the Google tab, press on the mic button, and it will recognize what you are saying in English, whether your accent is not just Indian, but it is Bengali or Tamil or Punjabi or Maharashtrian accent. It can basically all the pressure waves that are coming out of your mouth depend. Even though you might be close to the phone, farther away from the phone, you may have one kind of an accent, another kind of accent. You may have a higher pitch or a lower pitch, uh, and some intonations depending on your gender and age. All those, even with all those variations, it is able to recognize the words that you speak, and it is able to convert that into text, and it can do a search for you for that query. So all this is not possible by typing an algorithm or typing a model of converting pressure waves into word mapping. It is only possible through machine learning. Okay. Similarly, Now it is also being used in other fields such as finance, where your um, your credit risk score is based on certain factors such as your income, your your previous loan behavior, loan payment behavior, etc., etc. So it is this machine learning algorithms are being used in many places. Even if we talk about something that seems very unrelated, such as mechanical engineering, even their design of parts, design of materials, design of metamaterials. If you talk about biology and medicine, then design of drugs, again design of metamaterials, etc. A lot of that is now being done with machine learning. So machine learning has become an essential engineering tool for a vast majority of fields. Okay. Any questions? You can raise your hand, you can ask directly. Okay. All right. So yeah, so I mean, it should actually be a core course. Machine learning should be a core course, but here we are. Okay. Uh, so what you will learn in this course, right? So what are the objectives of this course? So these are some of the things that you will learn. First is you will assess whether a problem is suited for machine learning or not. Okay? We'll spend perhaps half a lecture on this. We'll look at what kind of problems are suited for machine learning, what kind of problems are not suited for machine learning. Then we will spend majority of the course time on the next three bullets, which is map problems to popular machine learning frameworks. So if you are given a certain type of input and a certain type of desired output, then what kind of a machine learning framework maps from that input to that particular type of output? Okay. So for example, if you want to, if your output is a continuous variable versus your output is a categorical variable, then you use different kinds of machine learning frameworks for that. So we will look at that. Then you will learn to precisely define and describe these models using words as well as mathematics. So you will be writing mathematical expressions to say what machine learning algorithm does, all right, and how it trains, what is the optimization process that is being that is responsible for training a machine learning algorithm. Okay. And then you'll learn to code and train these algorithms, compare them for time efficiency, for accuracy, etc. Okay. Then we will look at some basic proofs of guarantees in ML. This will be towards the end of the course. Okay, so first let's get the exciting stuff out of the way so that you can get on with your assignments and projects. And later on, we will cover some of the theory in slightly more detail. And we will identify directions for advanced machine learning R&D. Any questions?
Hello, sir.
Yeah.
Yeah, this is Sharnadeep. So I am working mostly in the nanoelectronics and VLSI domain. And as far as I know that nowadays machine learning is vastly implemented in these areas. So I mean, as you mentioned just before regarding metamaterials, so would you just briefly elaborate on what are the areas of semiconductor industry or maybe nanoelectronics and microelectronics where machine learning is these days applied largely?
Okay. So I am not fully familiar with how ML is applied in your field. What you can look at is some of the research journals that get published in your area, and on in that online interface, you can search for machine learning in their search box and see what kind of papers have come up in the last 3 years or so. But to give you an example, I worked with a professor in physics, where we had a joint student who designed metamaterials
Right.
for specific optical output. So basically
Harmonic
these.
applications, right?
Right, exactly. So basically, these are a set of problems called inverse problems, right? So what is a forward problem is that, let's say you have some system. So let's say you have a metamaterial, right? So you have a nanomaterial where you have imprinted some shape, and that shape repeats. Okay,
Right.
it's a very small scale, but that shape repeats, right? So this shape is defined by certain things such as what is the outer diameter, what is the inner diameter, and how wide is this crescent, for example. I'm just making this up. And
Okay.
if you have this etched on the surface, when light falls on it and it comes out, there will be some spectral change in that light, right? So this particular shape will have, it will polarize the right light in a certain way, certain at certain angles, certain frequencies will be suppressed, whereas other frequencies may be relatively uh, unsuppressed,
I
right?
mean, sort of
So
filter like
right,
operation, right?
sort of a filter, exactly. So let's say we have a desired, now if we have a desired uh, if we have a desired spectrum and we want to find out what shape we should imprint on this surface to have this spectral properties, the way you will do that is you will take thousands of uh, thousands of such shapes and put it in a physics solver to find out their spectra. Okay,
Okay.
so this will be your, so this will be your yi, and this will be your xi. Okay, so for lots of, so you can do this forward mapping using some physics simulation.
Right.
Okay, and then once you have that, you train a neural network to take this as input and give this shape as an output.
Okay.
Okay, so then you can give you even though you have not shown it this shape, hopefully it has learned enough information, enough ways of mapping from the spectrum to the shape, that given a new spectrum, it will find you the appropriate shape.
Okay. Okay. Fine.
So that's sort of the inverse anatomy of an inverse problem, solving that using machine learning.
Okay, sir. Okay, sir. Thanks a lot.
All right. Okay, so what are the prerequisites for this course? Before that, anyone else has any questions about what you will learn? Okay, so some of these highly specific applications of ML, I may not be able to teach in the class. So, but you please feel free to do that as a class project if you are interested in any specific applications. So the prerequisites for the course will be that you should know basic linear algebra, and this probably the first two things you already, all a lot of you already know. So basic matrix products, sorry, matrix operations and vector operations, such as matrix vector products, matrix matrix addition, vector vector addition, dot product. So these probably you already know. Okay, and then slightly more advanced things such as eigenvector, okay, and determinants, etc. So these hopefully you will know these also. Then intermediate probability. So this is not like discrete variable probability, such as if you have two dice and you throw two dice, what is the probability of getting a sum of 10, right? So those are for discrete variables, but here we will mostly be using continuous random variables. Okay, so we will be dealing with things like probability distribution. So let's say if this is x and this is p of x, and this area under this curve is 1, that means this continuous variable can take any value in intervals, and within those intervals you can define the probability of the variable falling. So a good example of this PDF, a very common example, is this Gaussian PDF. Okay, so we will be dealing a lot with these probability distribution functions, continuous distributions, and then also things like joint distributions, conditional distributions, and marginalization. Some of this I will cover quickly when we get to those topics, but it will be good if you refresh it on your own. And I will show you some resources towards the end of the class of what you can quickly revise this weekend. Okay. You should know basic calculus, derivatives of functions, finding maxima or a minima of a function, partial derivatives of functions of multiple variables. So these things you should already know. Chain rule of of derivatives. These things you should know. Okay, you should be very comfortable with intermediate level programming. Okay, so you should know what are loops, if then else conditions, while loops, for loops, how to make functions, call functions, how to use libraries, okay, how to work with arrays, indexing arrays, and so forth. Multi-dimensional arrays also we'll work with. Input, output, file input, output, plotting graphs, etc. So these are not something that we'll teach in class. We might post materials on where to learn these things from, but they will not be covered in lectures. Any questions?
Hello, sir.
Yes.
Sir, Zad here, sir. Sir,
Yeah.
I have a question. Is there any specific programming language that we are going to use in this class?
Yes. Python.
Okay, sir.
Any other questions?
Yes, sir. Sir, is this course going to involve a lot of mathematics?
It will involve some mathematics, yes. But almost all disciplines require mathematics in IIT, right?
Yes, sir.
So, yeah, it won't be like, I mean, I don't think it will be too difficult of mathematics. It will require some mathematics. So,
It's like how many assignment like you are going to give like
yeah, I'm coming to that.
okay, sir.
Sir, one more question.
Yeah.
Could you please tell us which packages exactly we are going to use? So we will.
Pandas, NumPy, okay, and scikit-learn. These are the main ones. And if you want, you can also use Keras, TF Keras, TensorFlow Keras.
Okay. Thank you.
Hello? Matplotlib. You'll also use Matplotlib. You will also use maybe something with images, right? So one of the packages that deals with images.
Okay, sir. Thank you.
So can we directly?
I'm sorry, can you repeat? Hello? Maybe type it in the Swandeep, did you already ask your question?
Yes, sir.
So someone else was speaking. If they have audio problems, they can type.
Yes, sir, I was removed by someone. Sir, can we use Anaconda instead of all this?
Can you use what? Anaconda. Yeah. So Anaconda it comes with these libraries. Anaconda is just an IDE, right? So it's you can use Anaconda.
Okay.
I mean, you might find it easier to use Jupyter notebooks on Colab, but it's really your choice. If you want to do it in Anaconda, that is also fine.
Like I have already Jupyter and Anaconda set up, so
yeah, yeah.
So I have a question.
Yeah.
Like, is there any prerequisite? Like, can we enroll in this course as an audit course? Because
Yes.
okay.
Yeah.
And are the assignment load and are going to be the same as that of the credit course?
I'll come to that.
Okay.
So these are the two main books: Pattern Recognition and Machine Learning by Christopher Bishop, and Understanding Machine Learning from Theory to Algorithms by Shalev Schwartz and Ben David. Both of these books, the authors have made it freely available in PDF form. This is the topic plan. We will start with linear regression, non-linear regression, sparse regression, and then we'll get into classification. Okay, so regression means you are predicting a continuous variable. Then in classification, you are predicting classes such as cat or dog, which is whereas regression would be a continuous variable. For example, predict the temperature for tomorrow. Temperature is a continuous variable. Okay, then we will look at optimization a bit in more detail. We look at feature engineering for some popular data types such as images, text, audio, etc. We will do a quick introduction to deep learning. I will not go deep into deep learning, pardon my pun, but here it's because I mean a lot of useful models, a lot of useful ML engines are basically now in deep learning. But the solid foundation in thinking about machine learning will also help you in deep learning. Okay, so don't jump ahead into deep learning just yet, but hopefully you will get a better appreciation once you go through the ML course. Then we'll get into combining models. So sometimes when you combine multiple models, it's like a committee of experts make better decisions than a single expert. So combining models will give better results. Okay, so we'll see some proofs and we'll see some ways to combine models. Then we will look at unsupervised learning. In unsupervised learning, we will look at how to reduce dimensions when you have too many variables, how to cluster data points. We'll look at modeling probability densities and one particular way of doing that using EM algorithm. We will do a quick introduction to graphical algorithms, reinforcement learning, and to learning theory, which is the theoretical part of ML. Okay. Any questions? Does it? Any suggestions or like is it? Any doubts about? Does it cover what you had in mind?
Sir, are we going to? Can we implement this machine learning at the embedded level, at the controller level?
Yes, why not? So, I mean, I won't teach you how, but hopefully you will get enough insights to attempt it on your own. Okay, so we will look at what is the memory footprint of a model. We look at how many computations a model requires, right? So those things will help you make those decisions about whether this can be implemented at the embedded level or not. Or do you need a simpler model in some sense? Okay.
So any topic that we particularly cover, sir, like I read about TinyML recently.
Okay.
Can we
I'm
give
not
a
sure.
touch?
Yeah, I'm not sure what that is. I mean, you can feel free to like drop a link in the general channel of MS Teams and I will take a look.
Sure, sir. Thank you, sir.
Sir, in introduction to deep learning, are you going to cover NLP, CNNs? I'll like.
Yes, basically this will include CNNs, and then it will cover this LSTMs or RNNs. Okay, I will not cover transformers. I don't think we will have enough time to cover transformers.
Okay, sir. Thank you.
Sir?
Yes.
Yes, sir. This is Somil here, sir.
Yeah.
Yes, sir. Are we going to cover transfer learning in this course?
No, I will basically talk about it very briefly here. And basically, I will just talk about copying weights, nothing more than that.
Okay, sir.
That's for advanced course. More deeper transfer learning could be for an advanced course.
Sir,
Yeah.
do we need a very good PC like that or for this?
No, I think if you are using Google Colab, the only limitation is that you need a continuous internet connection and then it shuts out after 12 hours. You have to restart it after 12 hours. So as long as your
Okay.
coding is not and your training is not going beyond 12 hours, you should be fine.
Yes.
basically how to get most out of this course, right? So when you are listening to pre-recorded lectures, you should take notes. Don't just like think of it as music in the background. All right, that doesn't help anyone. Okay, so make at least some handwritten notes while you are listening to these lectures. Okay, and then you can take a snapshot of that and upload it. Okay. So yeah, so listen to the pre-recorded lectures, take your notes. There will be no repeat of the recorded material. I will not go over the slides again. I will just show a slide and ask you what are your doubts in this slide. Okay, and then take a look at the books that and internet resources. I will post suggested sections to read, especially from the Christopher Bishop's book. Okay, attempt problems in the tutorial sections. Okay, discuss with classmates. So all that our TAs will keep tab of who's prepared and who's not prepared, and become very comfortable with programming. Okay, and then ask any doubts that you have with the to the instructors and the TAs. Okay, that's how you can get the most out of this course.